Hi, my name is Matt Link, and I was one of your team leads for week 9, where we modeled the spread of disease. And I'll be going kind of faster because I've been hitting the time limit, but so I'll be skipping over some steps or just kind of not talking about them as much. But here's the scenario. So with COVID-19 lingering around longer than a bad smell, many mathematical models are continually being analyzed to help forecast the future of the pandemic at local, national, and international levels. This pandemic is far trickier than anyone had predicted and has features that no single model has yet been able to pinpoint. Though the SIR model is a system of 3 differential equations that most Center for Disease Control and Prevention simulations start off with, we will consider a simpler variation of this more complex nonlinear model. In our model, we assume the following. There are 2 compartments. A person is either susceptible or infected. We assume that those who are susceptible can become infected, and we assume infected individuals can become susceptible again. So here's the differential equations that we are given, where S is equal to the proportion of the population susceptible, I is equal to the proportion of the population infected, where A and B are greater than 0 and there's some real constants, and T is the time since the outbreak was observed in days. And then S and I are just some proportions that are between 0 and 1. So our first step was drawing a diagram. And what I did is I just kind of looked at each term individually. So we know S, like this term, the S is the proportion of the population susceptible. And then we have the negative here. So that, to me, that just says that these are the people that are becoming infected, which makes sense because here you have the positive AS. And it's the same thing for the BI. This is the proportion of the population that's infected but is becoming susceptible. So here you just have the negative AS flowing out of the susceptible population and flowing into the infected population. And then you'd have the negative BI flowing out of the infected population into the susceptible population. So step 2 is making sense of the units. Here's some stuff we already know. And we know DSDT has to be equal to, in its units, it has to be equal to the proportion of the population susceptible per day. And so for each term, they have to be in those units. And if we were to look at like the negative AS here, for example, you have A times S, and its units are the proportion of the population susceptible, which has to equal this here. And the only thing that's missing here is per day, which means A has to be per day, where A is just some like proportionality. It's the same thing for B, where all you're missing here is the day, so B is per day, where B is some proportionality. Step 3 was understanding why ds dt and di dt equals 0 when added together. To me, I just kind of looked at this. If you have like a negative AS, so if you have like negative 10, so that's like 10 people who are becoming infected and leaving the susceptible population, you have like a negative 10 here, and you have a positive 10 here flowing into the infected population. And it's literally the same thing for the negative BI and the BI. If someone's becoming susceptible from the infected population, you have like a negative 10 here and a positive 10 here. So if you add them up, technically they should always add to 0. And if you look at this mathematically, you have ds dt plus di dt equaling 0. And if you add in what ds dt and di dt are equal to, you're going to get this, and the terms will cancel out and equal 0. So step 4a was finding the eigenvectors and eigenvalues and their importance. So first, we know is this type of equation, which according to Milos, it's first order homogeneous linear systems of ODEs with constant coefficients. We know it's first order because we only have the first derivative, and we know it's homogeneous and linear because we have no product of f of t or like sum of f of t. So in order to solve this, we'd want to get it into this form where we need a, and where y represents ds dt and di dt. So to get the matrix A, we're going to do what we've done before, where you're going to line up the same values and then you're going to put them in the matrix. We'll have negative A, B, and negative B. And if you plug that into Wolfram alpha, you're going to get the respective eigenvalues and the eigenvectors. So we know delta 2 is always going to be less than 0. This is because we know A and B are always greater than 0 from what Milos told us at the beginning. And then here, if A and B are always greater than 0 and you're subtracting them, this means delta 2 is always going to be less than 0. And this tells us that we have a sink. And then since delta 1 here is 0, that's like a special value, and it means that we will have an equilibrium points that are along the corresponding vector, v1, which is b over a and 1. So if you go and plot this in the phase plane grapher, this is kind of what you'd get. And then the vector that I was talking about, this is what it would look like imposed here. And these are all like equilibrium points along the line. It's just dependent upon your A and B values and your initial conditions. So step 4b was modeling S of t and I of t. So again, here's the values we got from before. And this is kind of like the main equation that we'll plug all these values into to get the respective equations. So if we do that, we'll have y equals k1 times e to delta 1. Delta 1 is 0. And then you'll multiply that by vector 1, which is b over a and 1, plus k2 times e to delta 2, which is negative a minus b, and then negative 1 and 1. And I should have a t there. And then if you multiply the vectors times these terms, you're going to get s is equal to b over a times k1. The e to the 0t just becomes 1, so it kind of cancels out. And then you'll have the negative 1 times k2 times e to the negative a minus b times t. Same thing for I. You multiply the I, you'll get k1 plus k2 times e to the negative a minus b times t. So step 10 was determining the particular solutions and graphing S of t and I of t. Here's just kind of a reminder. So if a and b are equal to 1, we're going to take our general equations we got for the susceptible population and the infected population, or proportion, sorry. And you're just going to plug in the a and b values. And when you do, it's going to simplify down into these two equations. And then from here, you're just going to take our initial condition where it starts out at 0.9 for the susceptible population and 0.1 for the initial population. And of course, t is 0. So this simplifies down to 1, and you should get k2 for each of the terms. And then when you plug this system into Wolfram, you find k1 is approximately equal to 0.5, k2 is approximately equal to negative 0.4. And if you go back up here and plug these k1 and k2 values in with your general equations that you plugged in the a and b values into, you're going to get these two equations right here. And then if you graph these equations, you can see that S of t and I of t both approach 0.5. And then if you do the exact same thing we did in the last step, where you plug in the respective A and B values, and then you plug in the initial conditions of 0.9 and 0.1, and then you solve for the K1 and K2, these are the equations you'd get. And then when you graph those on Desmos, you can see S of t approaches 0.667, and I of t approaches 0.333. Again, same exact thing as the last two problems, just with different A values and B values. These are the equations that you'll get. And if you graph them on Desmos, you can see that S of t approaches 0.333 down here, and then I of t approaches 0.667. So step 8 was comparing the results of these graphs. So this is just kind of what we got. So if A and B are equal to 0.2, S of t and I of t approach 0.5. If A is equal to 0.1 and B is equal to 0.2, S of t approaches 0.667, and I of t approaches 0.333. Same thing for these values down here. And so kind of the general formula I got for this, I just kind of fiddled around with it. I didn't do anything specific. I was just looking at, is there some value? Is there a value that they approach that is based solely on the b and a plus b values? And I found that S of t approaches b over a plus b, and I of t approaches a over a plus b. So if you plug in the respective a and b values here, so for example, if you plug in 0.2 into this equation for a and b and 0.2 into this equation for a and b, you're going to get 0.5 and 0.5, which matches here. If you do the same thing here, you're going to get S of t approaches 0.667, which is true. I of t approaches 0.333, which is true. And just the same thing for this problem here. So step 9a was using a limit argument as S of t and I of t as t approaches infinity for both of those. So if you do the limit of S of t as t approaches infinity, and you plug in S of t, you're going to get this. As t goes to infinity, this whole term here is going to approach 0, so it's pretty much going to go away, and you're just going to get the b over a times k1. If you do the same thing for I of t, this whole term here is going to go away since it's going to approach 0, so you're just going to get the k1 here. So step 9b was solving for k1 and k2. This is just kind of a reminder. So here, you're just going to plug in your initial condition of 0.9 and t equaling 0. And when you do that, it's just going to simplify down into this expression. And if you do the same for I of t, where the initial condition was 0.1 and t is 0, it's going to simplify down into this. And if you go ahead and plug that into Wolfram alpha, you're going to k1 is equal to a over a plus b, and k2 is equal to b minus 9a over 10 times a plus b. And then here, here's the general equation we got just a step before this, but you can simplify this term here. So if you do that, if you multiply this by b over a, you're going to get this, and if you factor out an a, it's going to cancel out, and you're just going to get b over a plus b. So then here's the respective equations you get when you do that simplification. And again, if we were to do a limit argument on this, you can see this whole term goes to 0. So S of t approaches b over a plus b, and I of t approaches a over a plus b, which is pretty much what we said in a few problems before this. So step 9c was doing analysis and graphing results. If we let a equal 0, then the disease dies off. Why? This is because, well, these terms will cancel out, and you just have a negative bi and a positive bi. So that means the infected population is always becoming susceptible, and there's no increase in this. It's just continually decreasing. So eventually it's going to go to 0. And this may not be possible to do because no one's becoming infected in this scenario. And give another way besides a equaling 0 to make the infection go away as much as possible. To do this, you'd have to have an infinitely large b value. Well, it doesn't have to be infinitely large, but here I have like b equals 10 and a equals 0.1. So b has to be large and a has to be really small. If you do that, then you can see that the susceptible population is near 1, while the infected population is near 0. And for this model, we are assuming that the population was fixed, that no one was dying, and that you're either susceptible or infected. You know, there's no third category for people who are immune. To make this model better, we just have to incorporate these things. And at the beginning, he did say that there's an SIR model that has the removed portion of it there. So technically there is a model like that, and we just have to include that. And that's it.